In mathematical logic, two theories are equiconsistent if the consistency of one theory implies the consistency of the other theory, and vice versa. In this case, they are, roughly speaking, as consistent as each other. In general, it is not possible to prove the absolute consistency of a theory T. Instead, we usually take a theory S, believed to be consistent, and try to prove the weaker statement that if S is consistent then T must also be consistent. If we can do this, we say that T is consistent relative to S. If S is also consistent relative to T, then we say that S and T are equiconsistent. Consistency. In mathematical logic, formal theories are studied as mathematical objects. Since some theories are powerful enough to model different mathematical objects, it is natural to wonder about their own consistency. Hilbert proposed a program at the beginning of the 20th century, whose ultimate goal was to show, using mathematical methods, the consistency of mathematics. Since most mathematical disciplines can be reduced to arithmetic, the program quickly became the establishment of the consistency of arithmetic by methods formalizable within arithmetic itself. Gödel's incompleteness theorems show that Hilbert's program cannot be realized if a consistent recursively enumerable theory is strong enough to formalize its own meta-mathematics, i.e., strong enough to model a weak fragment of arithmetic, then the theory cannot prove its own consistency. There are some technical caveats as to what requirements the formal statement representing the meta-mathematical statement, the theory is consistent, needs to satisfy. But the outcome is that if a theory can prove its own consistency, then either there is no computable way of identifying whether a statement is even an axiom of the theory or not, or else the theory itself is inconsistent. Given this, instead of outright consistency, one usually considers relative consistency. Let S and T be formal theories. Assume that S is a consistent theory. Does it follow that T is consistent? If so, then T is consistent relative to S. Two theories are equiconsistent if each one is consistent relative to the other. Consistency strength. If T is consistent relative to S, but S is not known to be consistent relative to T, then we say that S has greater consistency strength than T. When discussing these issues of consistency strength, the meta-theory in which the discussion takes place needs to be carefully addressed. For theories at the level of second-order arithmetic, the reverse mathematics program has much to say. Consistency strength issues are a usual part of set theory, since this is a recursive theory that can certainly model most of mathematics. The usual set of axioms of set theory is called ZFC. When a set theoretic statement A is said to be equiconsistent to another B, what is being claimed is that in the meta-theory it can be proven that the theories ZFC plus A and ZFC plus B are equiconsistent. Usually, primitive recursive arithmetic can be adopted as the meta-theory in question, but even if the meta-theory is ZFC or an extension of it, the notion is meaningful. Thus, the method of forcing allows one to show that the theories ZFC, ZFC plus CH and ZFC plus CH are all equiconsistent. When discussing fragments of ZFC or their extensions, the notions described above are adapted accordingly. Thus, ZF is equiconsistent with ZFC, as shown by Gödel. The consistency strength of numerous combinatorial statements can be calibrated by large cardinals. For example, the negation of Kuiper's hypothesis is equiconsistent with an inaccessible cardinal. The non-existence of special Aaronson trees is equiconsistent with a Marlow cardinal, and the non-existence of Aaronson trees is equiconsistent with a weakly compact cardinal.